Hey guys, thought I would try to do a video or lecture with my face on it, so y'all don't forget what I look like. Hopefully, give you some reassurance that we're still okay, still hanging in there. Alrighty, so this video is going to be part one of discussing comparison tests. Okay, so there are two varieties of comparison tests. The first variety is just called the comparison test. So here's the drill. So suppose we have some unknown series, so a series we know nothing about in terms of convergence. We're going to call that series A-sub n. And that series has positive terms. So that's all we know, is that it has positive terms. All right, so now let's also suppose that we have a known series. So a series that we totally know the convergence of. Or even if we don't know it right off the top of our heads, we could find it. And we'll call that series B sub n. And that also has positive terms. So that's sort of our starting point. And here's how the test works. So if all the terms A sub n are smaller than the B sub n's, and we know that my series with B sub n converges, then I know that my series with the A sub n terms also converges. Okay, so that's good. And if my B sub n terms are smaller than my A sub n terms, and I know that my B sub n series diverges, well, then that tells me that my A sub n series also diverges. Although I guess I don't know why we have the word also in there. I mean, why I have the word also. You might think at this point that I'm using the tablet, but I'm actually using a newer contraption. So hopefully this makes sense to you. And just as usual, to clarify things, what can I tell you? Examples are us. So we're going to determine whether the following series converge or diverge using the comparison test. And so here's how we rock. Okay, so first of all, we have the summation 1 over n times n plus 1 times n plus 2. So I hope that you agree that this has to be less than or equal to at the very least. And, in the comparison test, we're actually allowed to have equality. I should have really mentioned that. So it could be less than or equal to. Anyway, back to our example. This is less than or equal to 1 over n cubed. We know this is true because I'm multiplying n times a couple things that are larger than it, which means that the denominator is bigger than n cubed, and a larger denominator means a smaller fraction, if the numerators are the same at least. And do we know anything about the summation n going from 1 to infinity, 1 over n cubed? If you said it converges, then you are absolutely correct. Why does it converge? Anyone? Can I picture people shouting out answers? It's because it's a p series with p is equal to 3, which is bigger than 1. And so since that is true, that means that my given series converges. Let me see. There we go. Can we just pretend I didn't make that a capital so that it's grammatically correct? Okay, so if you have any questions on this one, make sure you write them down so you can ask me during office hours. All right, second example. Okay, so I'm going to take this one slowly. So first of all, does everyone agree that I'm not super great at this? No. Does everyone agree that 2p minus 1 is less than or equal to 2 times p? Anybody disagree with that? I'm asking questions like you're here to answer them. Okay, so if I take the square root of both sides, then then nothing changes. Okay, so in other words, I can say that the square root of 2p minus 1 is less than the square root of 2 times p to the 1/2. Well, what does that mean? That means that when I do a 1 over, right, the sign switches, which means that I'm getting, nope, that was fine as is. I'm getting confused in my old age, huh? All right, so that's great, that's great, that's great. Now what? All right, so since this is true, now let's look at the summation n going from 1 to infinity of 1 over square root of 2 p to the 1/2. So first of all, 1 over square root of 2, we can write that as a product of those two. I don't know why I'm having this n thing going on, but p. I'm sure several people are mentally correcting me as I'm writing these silly things incorrectly. Okay, so we can pull out the constant because it's just a constant. And what do we know about this guy? Right, we know this guy diverges because, again, it's a p series, but what is our p this time? I dotted my e. Don't dot your e's, dot your i's. P is equal to 1/2, which is less than 1. And so that means that the whole shooting match diverges. So here we go. Since this is greater than or equal to 1 over square root of 2 times p to the 1/2, and that series we just established diverges, what does that tell us? That tells us that our given series also diverges. So this is just straight out by the comparison test. I feel like I left way too much room for example 3, don't you? Well, this is going to be fun. Oh, no, wait, there is room. Duh. So there is an easier way to do this problem that I'm the 1 over k factorial, and that's the ratio test, but we're supposed to use the comparison test, so we'll use the ratio test later. Alrighty then, 1 over k factorial. What the heck am I going to do with a 1 over k factorial? So what you want to remember is k factorial is going to be k times k minus 1 times k minus 2, etc., all the way down to times 2 times 1. And this is going to be greater than or equal to 2 times 2 times 2 times 2. How many times? That's a good question. Times 1, of course. And this is 2 to the k minus 1. Right, so this is what we have right now. We have k factorial is greater than or equal to 2 to the k minus 1, which means that 1 over k factorial is going to be less than or equal to 1 over 2 to the k minus 1. All right. So let's do this. Well, that's for k greater than or equal to 2, I should say. Where'd I go? What about k equals 0 and k equals 1? And for k equals 0, if k equals 0 or k equals 1, 1 over k factorial is 1. Okay, so we can look at the summation as k going 0 to infinity, 1 over k factorial, we can look at as 1 plus 1 plus the summation k equals 2 to infinity of 1 over k factorial. All right, so now all we have to do is look for the convergence of this guy. Well, here we go. So since 1 over k factorial is less than or equal to 1 over 2 to the k minus 1 for k greater than or equal to 2, and what do we know about this guy? Well, this is 1/2 plus 1/2 squared plus 1/2 cubed plus, which we can look at as summation k going from 1 to infinity, 1 over 2 to the k, which we can also look at as 1/2 to the k. And this is a geometric series. You remember those, hopefully. And r is 1/2, which is less than 1. So for a geometric series, that means it converges. Since this is true, this series converges. Adding the two terms doesn't do anything to us. So that also converges. And so our original series also converges. I don't know what the so is for. At this point, you might want to pause, take a moment, and think about this. I know you might argue a geometric series starts at k equals 0, but we've already talked about that if the series, if part of it converges, adding a few terms doesn't change convergence. So here's the idea, the drill now. This does not always work, this comparison test, right? You can end up with problems where it doesn't work, even though it's the easier of the two to use. So what do we do then? Well, we're going to be having to use the limit comparison test. So I think I'm going to start the limit comparison test, and then I'm going to call it a video, and we'll do it next time in the next video. Okay, so sometimes it's not quite enough to determine if a series converges. We do the limit comparison test. What is the limit comparison test? Well, it's a bit of a pain, but we can do it. So here's how it rolls. So let's suppose now that I have two series, a summation a sub n and b sub n with positive terms. And it's called the limit comparison test because I'm going to take the limit as n goes to infinity of the a sub n over b sub n, and let's just say that that equals some limit L. Now that limit L may not be finite, I'm just throwing it out there to give it something we can talk about. So if L is finite, then the series either both converge or both diverge. So they behave the exact same way if that limit is finite and positive. If the limit is equal to 0, and we know that B sub n, the series with B sub n converges, then we know that the series with A sub n converges. And if the limit is infinite and the series with B sub n diverges, then the series with A sub n diverges. And I think this is an awesome place to stop. And so I am going